Okay, let's get going today. So the main topic I want to cover today is some details about the reason for the formation of extended one-dimensional defects as dislocations, and going through some of essentially want to connect the microscopic origins of strain to reasons for strain relaxation, and then why dislocations form, and once they form, what are the consequences. Primarily, what are the consequences on electronic devices or photonic devices, transistors, LEDs, lasers, and we'll see that typically if you can avoid them, obviously that's the best situation. But if you can't, you can actually make use of them to create heterostructures that would otherwise be impossible. So that's very much of a reason to be able to use to use dislocations, and we'll see some very clever ways also of using dislocations to get rid of defects and impurities, which is another thing that comes about once we understand why is it, what are the energetics of the dislocation, what is the microscopic picture. So that's really what we're going to cover today. Okay, so there's one more thing before I start. I realize we have no class next Tuesday. I'm actually traveling just next Tuesday. We'll have a class on Thursday, and I don't want to have too many more makeup classes in the end of the year, end of the semester. So is this Friday something that would work for you? Same time, 6 p.m. here. Yeah, I think Friday evenings. I generally don't want to do this, but I realize that it's difficult otherwise. Looking forward to the future. That's tomorrow, actually. Yeah, tomorrow 6 p.m. Will that work? Okay, so I'll send out an email in case some of you not here, in case there are any major reasons not to have it. I'll rethink, but let's say that it's 6 p.m. tomorrow. Okay, so. Okay, so what we'll do today is before I start, any questions? What we're doing in the last class is looking at strain from a microscopic picture, and essentially what we ended up was with the very classical arguments of energy being, essentially half kx square sort of picture because of atoms, because of bond stretching and bond bending. You end up with a certain energy for an alloy, and the net energy that minimizes the formation of tetrahedra of different alloy compositions, right, is given by this valence force field energy scale, right? That's what we came up with in the last class, and that looks basically a constant times delta x squared. That's the kx squared sort of picture. And what is really amazing is it's almost a classical picture, but then because these parameters that we talked about, the alphas, which were the bond stretching energies, and the betas that were the bond bending energies, spring constants, not energies, they've been experimentally tabulated, so it's not like these are not first principles experimental, but you can also calculate it now using first principles DFT fully, from a quantum mechanical perspective. But once you know them, that's extremely useful, because you can calculate it, and it's no wonder that you are getting very good fit between experimentally evaluated energies for this sort of microscopic strain. The experiments and the model are in very good agreement for many classes of 3-5 alloys. So today, what we are and we had already started talking about a bit about strain in the macroscopic picture, and we are going to essentially connect that microscopic image to macroscopic image, and essentially we will actually start from this. By the way, I said I will post a set of notes from maybe right after class today. I'll post a set of notes from Jeffrey Sau's book. This is a book on molecular beam epitaxy, primarily MBE growth, but it goes into quite a bit of detail of strain and energetics of dislocations and such things. So I'll post that chapter, and you can please read it. So that will also help with the problem 3 in your assignment, the sort of prelim exam as well, which is very similar to that paper that I had, you're looking at. Okay, so what we'll do is the question we are going to ask now is that if I have we'll ask it from a very almost utilitarian perspective, that I have a certain semiconductor and I'm trying to grow an epitaxial layer of some other semiconductor on top of it, right? So and there's a lattice mismatch, right? And because of the lattice mismatch, can I still grow a perfect semiconductor layer with no defects, or will I be forced to have some defects? And that will be dictated by all the energy arguments again, right? Any configuration that has a lower energy will ultimately be the most stable situation, and whether you will reach there or not will typically be dictated by kinetics, right? Whether the minimum energy is something, but then whether you reach there or not will depend on how fast you can get there, right? So that's the other aspect. But we are going to focus today a little bit more on the energetics and find what are the minimum energy configurations, and then that will tell us what sort of dislocations will you form, what will be the density, and that sort of thing. So that's what we're going to look at today. We will basically be looking at right now a strain in epitaxial layers, which can take actually many forms, and I'll indicate what I mean by that. Right? So strain in an epi layer could be that I have a flat in a substrate of, say, gallium arsenide or gallium nitride, or any semiconductor, actually silicon for that matter. So this is your substrate. Let's call it substrate. And then on top of it, I'm trying to deposit now and grow a very thin layer, or not necessarily thin, but a layer which has maybe a little larger lattice constant or a smaller lattice constant. And I'm sketching this in a macroscopic picture now, but this is an epi layer, right? That's one form of trying to grow a heterostructure. This layer has different lattice constant than that. The other possibility is I have actually these days there's a lot of interest in two-dimensional crystals. So let's say I have some two-dimensional crystal A, maybe graphene, and I'm trying to grow laterally another layer B, which may be something else, boron nitride, something like that, or moly sulfide and tungsten selenide, or something like that, right? So we're going to grow that, right? And let's say now the lattice constants of these layers, typically these are not necessary, but typically these are hexagonal lattices, right? And so let's say one of them is a smaller, well, there's a lattice mismatch between the two. So, and I will not talk too much in detail about this because this problem is still evolving. People are still trying to measure these things. Actually, quite a bit of nice work going on here at Cornell as well, trying to figure out how dislocations form, what are the strain fields, and all that kind of fun stuff there. Yeah. This has been looked at in great detail and still being looked at. It's not like the problem is completely solved, meaning the three-dimensional, because of all the transistors, LEDs, lasers, and photodiodes, solar cells, all kinds of stuff. So this is a very important problem in many of these applications. And this is a very interesting scientific problem. Essentially, we're going to talk a lot about 3D, but the same concepts will really go over to 2D. And I'll point out a couple of things that would be different in 2D. I think you can already see here your interface is 2D. Here interface is 1D, right? And here you really have, for example, here you have one freedom that you kind of don't have there. Your atoms can move in and out of the plane, right? And here you're kind of constrained in all three, right? So things like that. So this has some more propensity to form ripples and all that kind of thing. So instead of forming defects, it can still be accurate, but it will corrugate in that direction, for example. So there are little nice things about it. And a dislocation looks very interesting here because you can imagine it's very hard. Yeah, okay. So I'm not going to talk too much about 2D. Maybe later on I might give you a little problem or something like that on thinking about the 2D part. But let's look at a three-dimensional problem. And we are going to start by saying that, well, I'm looking at a lattice constant of, let's say, a epitaxial layer, a substrate, that's the lattice constant of the substrate, and a epi is the lattice constant of the epitaxial layer. So, and remember, these are related to the A would be the full lattice constant would be related to some bond lengths and all that, right? D was the bond length between indium and arsenic. And then, so depending on the crystal structure, the lattice constant is related to the bond length, right? And so we had looked at that. So that's one connection to the microscopic picture, of course, but A is really a microscopic quantity, the lattice constant, right? And so now you can think of, once we try to deposit this layer on top of this, there are various possibilities. One is this will go in as its own lattice constant, right? It will go in as this full lattice constant, it will be mismatched with that. Right? So right away, you can see that, for example, you may, for over, say, 5 nanometers, you may have 10 of these, or 5 of these, you may have 6 of these over the same length scale, right? So there will be broken bonds right away, because you can't, just counting the number of atoms, you see there must be some broken bonds here, for example, right? So that would be a completely relaxed situation. Or it can be completely strained, meaning it will conform so it will compress itself in this way, so that the number of atomic lattice spacings here becomes exactly equal to that. And now we are going to build in some the moment it starts to conform and there is strain, right? And you can see this is some form of a macroscopic strain now over the whole layer, over the whole wafer. This is the 4-inch wafer, 8-inch wafer, the whole wafer. This thing is going to be strained, right? So if you strain it, I think you know also from very intuitive picture that if you take a solid and you try to apply stress in this direction, then it will try to expand in that direction, for example, right? And all those. So those things are taken care of using these the Young's modulus and compliance coefficients and that sort of thing, right? So the most so let me first write down, instead of writing it as just bulk materials, again, this could be silicon, could be gallium arsenide, any of these we have talked about, so silicon carbide, if you might, or any elemental or compound semiconductor, and top of it I'm growing something which, let's say it's an alloy. It could be indium gallium arsenide, could be silicon germanium, or any of these alloys, right? So there's a lattice mismatch between, say, this and this, or this and this. You can grow indium gallium arsenide on silicon too, and then there will be both lattice mismatch and chemical nature mismatch completely. So you go from silicon to indium gallium arsenide. The atoms are completely different, so that sort of thing. So what we are going to do is start by just saying that here's the substrate, and I'm going to actually assume that the substrate is also an alloy. You don't have to think of it as also necessarily. I wrote down these things, but you don't have to have. I mean, you can have indium gallium arsenide here too. It's just that bulk indium gallium arsenide substrates are not available. So the idea is you have somehow managed to grow a certain indium gallium arsenide layer, and we're going to talk about that. It could be called a metamorphic layer on something else. And by the time you're on the surface, there are no defects left at all. You somehow managed to get rid of them all. So now it has relaxed, it has a certain lattice constant, and we're starting with saying that the substrate has a certain lattice constant. Again, the X substrate could be 0, in which case you would be looking at gallium arsenide here, for example, right? And that's a simple picture. And then the epi, the epitaxial layer now is what we are asking, and the A is the lattice constant. Now, right away you see, because of these compression and extension in this direction, or if you tensile strain it this way, it will compress in that direction. There will be, so it has its equilibrium lattice constant, right? But then once it goes in on top of another substrate, because of strain, its lattice constant is going to change, right? But it will change in two directions. One is this way, the other is that way. There will be two, right? So therefore, we are going to write that as one of them is parallel to the interface, right? This is parallel, and the other is perpendicular, right? So basically all we're saying now, and this is I don't think we have to really make too much difference, but if it is completely strained coherently, the word being coherent, the word coherent meaning there are no defects, everything is exactly matched, it has strain such that it matches up exactly with the substrate. In that case, that is equal to the in-plane lattice constant of the substrate, and the in-plane lattice constant of the substrate or the epi has become exactly equal to that of the substrate, right? So that's the so right away that says that in that case your epitaxial layer is strained. Right? Now, so now how much is the strain, right? The strain will actually depend on what are the thicknesses of these two layers. And then the way to look at it again is, I think you can, I can say that the strain is epsilon, which is, let me first write that. Strain in general would be, the new lattice constant minus its original lattice constant divided by its original lattice constant, something like that, right? How much did you change, right, because of the mismatch? Now, here, if the substrate itself is very thin, it is about the same thickness as the epitaxial layer, then both will strain. You see that? I mean, it's basically this will compress and this will stretch out. So the substrate is, and that ratio is really dependent on the thicknesses of the two layers. So if I'm growing only 5 nanometer over a millimeter thick layer, then obviously only this will contain all the strain. It's basically just like this can be thought of as a very, a spring with a very low spring constant. This is a very strong spring constant. It is hard to, strain, and therefore all the energy goes into the lighter spring or the weaker spring. So this is, and that's the one we're going to consider. There have been many ideas. For example, people have thought about having very thin layers on top of, say, amorphous or a more flexible layer, which would be like a SOI sort of technique, where the substrate can also strain. Those would be called compliant substrates and such things like that. We are not talking about that right now. I mean, there are some details. For most situations in 3.5 we'll be encountering, or when the substrate is relatively thick compared to many, 100 or 1,000 times thicker than this one. Actually, much more than that. And so we're going to say that the strain is all going there. In which case, so Sao writes in his book, the epitaxial strain in parallel is when, for example, this is it would be an example when both of them strain equally, and the okay. So let me write that now. The strain, and let's see how I'm writing. The strain again is directional. The strain in this direction is different from the strain in that direction. So, yeah. And they'll be related through this Poisson ratio and all that. We're going to do that now. But essentially, strain in the epitaxial layer, right, in the parallel direction, parallel to the plane or the interface, is equal to, well, it's you can write it as A epi, its new lattice constant minus its old original lattice constant, AP, 0, which was the unstrained part, divided by. So I'm going to just say that this is very thin, in which case it should be just A, AP, 0, right? It's unstrained value, right? But if you had, remember, this is the assumption here, that this is a very thin layer. If, on the other hand, the substrate was also thin, then you have to do a little bit of difference. So essentially, the number will be slightly different. It will be an average here. Okay, so now this is the strain in the plane. And now the questions we're going to ask are, well, in that case, what is the strain in the epitaxial layer perpendicular to the layer? What is that, right? And we know that strain is effectively the, kind of the delta x of a spring, mass spring system, right? The strain. And I think we know that the force in a mass spring system goes as some minus k times x, right? You stretch a spring. Similarly, and if you divide it by the unit area, that would be kind of a pressure, right? And you can absorb this sort of area over here, or you can write it as delta x, or by x naught and times some L. If you have a cross section area of the spring, then the length and the cross section essentially all this stuff can be absorbed here, and you get some sort of a constant, and that's your strain in a spring, for example. So essentially we're saying that the pressure is equal to some constant times the strain, right? And I think this is in linear elasticity theory, the stress. So this is called the stress, right? Stress is equal to some compliance coefficient times the strain. Stress and strain are related that way, and this whatever thing sits here has units of pressure, because strain has no units, right? So, is that clear? So you have these C's, and I think you see that that's what appears, and both of them actually, stress and strain. Just from this simple picture, you realize they're they're actually tensors because they have magnitude, and you can ask in which direction is this, right? So they're tensors, and they are related by this. Let's say. So I'm going to just write that down. In a cubic crystal, you can have stress in the x-axis, y-axis, or z-axis, right? And these will be called normal stresses. This will simplify a great deal, but perhaps you have seen it in some courses. So epsilon along the x, epsilon along the y, epsilon along the z, right? So these are the normal stresses. So for example, we just wrote down epsilon parallel, you know, and then if I label my axes as z, x, and y, right? So this one, for example, could be x or y. It's the strain in the plane, right? In the plane, xy plane. Right? And what it's going to tell us right now, the reason we are going through this is going to tell us now what should epsilon along the z direction be. It will tell us because it will be these compliance coefficients, etc., end up giving you the solid's response, the response of the solid to external pressures, right? So these are normal strains, meaning perpendicular to the surface. But then you can have a strain that twists the solid, right? You can have a strain. You can take a solid. The normal strains are the xy planes are like that, right? But you can actually apply a force that's not normal to it, but at an angle, right? So you can apply forces like that. So that would be shear, right? It will try to twist the solid and apply some sort of a torque here, and that, at least in this notes, is labeled as tau. It's a shear strain, right? So twisting, not just compression and dilation, but twisting. And now you can see there will be two zx. Okay, so there will be three possible orientations or angles, if you might, right? So and similarly, you will have the shear, so these are shear stresses, shear strains, and strains are labeled here as x gammas here, yz and gamma zx. You can see this thing will kind of be similar, but you have to rethink a little bit if you're talking about 2D crystals, right? Two-dimensional crystals. So rethink a little bit what exactly do these mean. You know? Okay, so. And then you have a set of coefficients here, and the set of coefficients that you end up, in general, you have, I don't know, maybe somebody knows 21, right, depending upon symmetries and all that for 3D. But then if you are in a cubic crystal, what you end up is basically there are three independent compliance, this C coefficients. There are only three in a cubic crystal, and those are the first three will be, the first three diagonal elements will be the same, you know, just C11s. Remember, the units will be a certain Newton per meter square. It's a pressure unit, right? Or pascals or gigapascals. I mean, the units generally are in that order. And then these three here would be the same as well. The shear components are the same. And these are measured and tabulated for pretty much all, you know, semiconductors now. And then the off diagonal elements are all 0 here and all 0 here. And I'm not going into all the detailed reasons why. And the off diagonal elements in this block are all the same as well, you know, for a cubic crystal. Just remember what we're talking. So we just write it as C12s, all of them. Sorry. So right, these are all the same. These are all the same. So you have basically three parameters pretty much. Now it really depends x, y, z. So you remember, if you're talking about a cubic crystal, silicon, gallium arsenide, indium phosphide, then you know, this is some artificial label we put in x, y, z. The real crystal structure can be oriented. For example, this surface, this direction could be the 1, 0, 0 direction of the crystal, or it could be 1, 1, 0, or it could be 1, 1, 1. You know, so it depends. If this direction is the 1, 0, 0 direction, then there's further simplification of these. If that's the 1, 0, 0 direction, if the epitaxial flammable substrates are oriented along any of the 1, 0, 0, meaning 0, 1, 0 or 0, 0, 1, then there is a further reduction in the because of symmetries in the matrix size here. and what you end up getting is essentially just two terms are left in the end, and those are the two terms we're interested in. What is the parallel strain and what is the perpendicular strain? Those are stresses and strains. That's all we are interested in at this point, at least. At the very end, so this whole matrix now shrinks again to this quantity, that the stress in the epi layer parallel and stress in the epi layer perpendicular is equal to, and maybe you can see how it's come about. You basically are summing over a few of these here, and then it just reduces to, and if you look at it a little bit carefully, you'd realize this must be the case, but and all that. But so C12 and C11. So, and here again we are. All right, so I don't think I'll try to say anything in detail about this, but that's how the stress and strain are related now. This is a very simple end result. And this is kind of a starting point for some of the discussion we're going to talk about today. This is essentially saying that the epitaxial layer has a stress in this direction that goes as this coefficient times strain in this parallel plane plus this times the strain in perpendicular. And then that's how it gets correlated because of strain, or rather, if you can see from here, you can invert the matrix and say that epitaxial strain in the parallel plane is it will become dependent on stress in the parallel plane in the parallel direction as well as the stress in the vertical direction. Right? So both are interlinked now. Right? So now what we can say is if this layer, now we're going to use some boundary conditions. If this layer is the top surface, it's not a buried layer, it's a top surface. There's nothing on top of it anymore. I mean, it's free on the top. If something is free on any side, then one of the things you can use is that in the vertical direction, the stress, which is the pressure, right, because it's free, the stress in the epi layer in the perpendicular direction, what will that be? If it's free, there's no stress. Right? It can relax completely in that direction. There's no pressure. So that is actually 0. Right? Because it's the top layer. You can't write it if it's a buried layer. Right? So, but if it's a top layer, meaning free on the surface, then this is 0. As a result, this thing goes to 0. Right? That goes to 0, and you can write down a relation now that 0 is equal to this times that plus that times that is 2 C12 times the epi strain in the parallel direction plus the coefficient 1 1 times epi strain in the perpendicular direction. Right, so that much you can do. And now that you got something that we were actually asking earlier, that what is the strain in the epitaxial layer in the perpendicular direction? Well, that is minus 2 C12 over C11 times epitaxial strain in the parallel direction, right? Is that clear? So you get that. If you know these material coefficients, you got the strain in the perpendicular. So now this is something we know because we are trying to grow a certain layer of a certain lattice constant on top of another. So we know the in-plane lattice constant, in-plane strain. Right? Is that clear? So what we did, I mean, just relating it to, so these are macroscopic parameters. People take the crystal and they'll actually strain it and see how much force is necessary, right? They put it under diamond anvils or water, pressure, and pressurize it and see how much. Basically, they'll apply pressure. Experimentally, we can apply pressure and see how much it deforms, right? That's really the experiment that's being done. And these are your spring constants in the end, right? So we just made that connection somewhere there. Right? Okay, so I haven't gone through this in detail. It's generally covered in courses on solid mechanics. Have you seen these before? Most of you. Okay, good. So I'll not try to belabor this, but essentially this is what I was after. And then now we are going to step into questions of energetics. Yes, this is the strain, therefore, and then what is the energy cost, right? And then things like that. And similarly, you can just write down if that's the epitaxial strain in the perpendicular direction, then in the epi layer, what is the perpendicular lattice constant, right? Perpendicular lattice constant. How do you get that? I think so you actually have. You can see here what you have is two things. One is this is 0, and the other is this is something you know, right? And you have two equations. You solve it, you will get that. You will get that, right? And if you get that, you know your lattice constant in the perpendicular direction too, right? So everything is known now. Right? Two equations, two unknowns. Everything. So just be clear what we know, right? These two things we know. Only for a free. So once you put, and many times we'll be actually growing quantum wells. So in that case, there'll be a strained quantum well, and then on top of it, the substrate comes back again, right? In that case, it will be slightly different what we wrote there. Right? Is that clear? So if you're growing a strained quantum well, the top surface is not free, in which case I can't put this to 0. Things like that. Okay, so now let's ask the question that yes, I've identified my epsilon epi. I know these things. Perpendicular. Now, what is the energy cost of this whole doing? Rather, we are going to ask this question that if I had a layer of a certain thickness here, say h of this epi layer, and I had a substrate of very much larger thickness, and they were separate, they were completely in their unstrained situation. This has a certain energy, that has a certain energy. Right? Take the sum of the energies, the whole thing separately has certain energy. Right? Now I'm trying to put this down, and I have realized that in order to get it to be coherent or strained, there must be a cost of energy to be able to do that, because in their relaxed states they are different. So now what is that cost of energy to be able to grow h nanometers of this epi layer 3,5 or compound semiconductor on top of that? What is that extra energy? That's what we're going to ask, right? And then we find an expression for that, and the energy expression, big surprise, will be half kx squared in some sort or the other. It will be like half some c's times some epsilon squares, and we already know all the epsilons, right? We already know all the c's, right? So there's, in the end it will be some combination, right? In fact, you can write it down even intuitively and you'll be correct. So it should be epsilon parallel squared in the x direction times half some c11 and c22, right? And epsilon in the y direction plus epsilon z direction square times certain c's. That's what it's going to be in the end. Right? That will be the energy cost of remaining coherent, and it will increase linearly with the thickness, because the whole volume that's being strained, not just one plane or anything like that. And then we'll see that there will be another possibility that instead of straining completely, it can actually form these defects or dislocations where there will be broken bonds here. Right? And we'll ask the question, what is the energy cost of forming those defects? Right? And then as you keep growing this thicker, the energy we'll find is the energy cost of the of remaining coherent, which will be this half kx squared term, will grow linearly with the thickness, but the energy cost of forming defects will grow only logarithmically, very slowly, almost remain constant if you might. Right? So at some point of energy, I think maybe I had sketched something in a hurry last time, but essentially what we're going to do now is find the energy cost of remaining coherent because of strain is going to grow linearly with h, whereas that of forming dislocations will kind of be something like that, logarithmic growth. Right? And therefore, beyond a certain thickness, which we'll call the critical thickness, it is more energetically favorable to form defects rather than keeping your strain, right? Keeping it coherent. Right? So that's really what we're going to do now. Right? What is that critical thickness? And again, not going to be a very big surprise. It will be off the order. It will be inversely proportional to the strain, as you might imagine. If there is no strain in the epi layer parallel, you can keep going forever, right? There's nothing to talk about if there's no strain, really, right? And all that. And then we'll see that now. Okay. So let's look at the energetics of it. We already talked about the strain, right? Okay, so the energy cost of stretching a spring is half kx squared. But again, if you take it to a solid, the energy cost of a solid being strained is basically a half a stress times strain, right? This is something you probably have seen too. The energy cost of straining a whole solid, because the force we saw is minus kx, and energy is integral of the force times dx, so that's kx squared by 2, right, for a spring, x being the displacement. And similarly, what we saw is the stress is some some of these compliance coefficients times the strain, and therefore the energy cost of being strained is well, let's write it this way. He uses notation U, and that is, let me just say that in general it is just that. In general, I'm writing it. You can write it in a tensor notation with xyz's, repeated indices, summed, all that kind of stuff. But in the end, this is how it looks, right? And hopefully you realize the units and all are sorry, what am I doing? Yeah, half sigma. No, what did you do? No, stress times strain, right? That's right. So is that correct? Yeah. Okay, so well, really nothing much to do. We know everything now already. We know already what is we know all 4 terms, right? Just sum them, multiply them, and sum them, okay. And then that's the total strain, and that's what and it's written as external and I. Let me explain what these mean, right? Or U I external. So the strain is being applied here in this layer due to external circumstances, meaning this layer, because I'm trying to grow it on this layer and it's trying to conform, the strain is because of that. It's not internal. Remember, there is also microscopic internal strains. Microscopic internal strains are something we talked about in the last class, which is saying that, well, if you grow indium gallium arsenide, let's say it's a 50% alloy, but then some parts are 30%, some parts are 70%, let's say. And then the tetrahedra are strained. This is what we are calculating in the last one. Those are microscopic strains, right? This is something that has come about because the crystal is trying to grow on something else, so it's external strain. Right? Just like in a crystal or in semiconductor, you have internal electric fields because there are atoms, there are charges. You have huge variations of electric fields, going. But then you apply contacts on it and you apply voltage. You have external field now on top of it, right? Exactly in the same way. We talked about microscopic strains earlier, and now this is external, right? This strain is external. It's coming out from outside, right? So the external strain energy, therefore, is so the way it's written here, as you see, is half times. So the I here is basically what it's saying is the ith layer. So you can have more layers on top and that sort of thing. But let's look at that in this way. So essentially, I can write it as half sigma perpendicular. Stress perpendicular times epsilon, write it properly, epi layer perpendicular times epsilon epi layer perpendicular. So that's in the energy cost of kind of stretching in that direction, plus half epi layer parallel times epi layer parallel. But then I think you just realize that this is there should be 2 of these, one in x and the other in y. That's all there is to it, and then so there will be no half here. That's what it is. There will be 2 of that. And after you write this all out, just take these expressions from here, C1, 2s, and all that, plug it back in, and you end up with this expression that it's C complies rather the C. Let me write it this way. Whatever is written there, plus CI 1, 2. Right, so and this goes as epsilon I parallel squared plus, once you sum this all up, 2CI 1, 2 perpendicular is 2, okay, and then half CI. Is it clear what we did? Essentially, I just took this formulas for, I mean, that we derived for epsilons and sigmas, all the knowns, and plug them back in here, right? So this is what you get. The i's here, just to be clear, so the I is, remember the compliance or the C coefficients have been measured not necessarily for an alloy as much as for indium arsenide, for gallium arsenide, you know, the binary components, or indium nitride, gallium nitride, or silicon and germanium. These have been measured for separately. So if you are trying to grow, let's say a silicon X, germanium 1 minus X, let's say, right? Then the C11 for that alloy, right, will be C11 or X times C11 of silicon plus 1 minus X times C11 of germanium. Do you see what I mean by that? So essentially, you just have to take care of that. You know, the C's are ones that are for the epi layer, not the individual components, but the epi layer. That's why we have these I's and all that. So, okay, so. So that's the energy cost, and we are going to. So that will be one term in our whole business of. So this is basically going to be the coherence energy cost for remaining coherent and strained. I think we can kind of use this. It's a big expression, but actually the physical meaning is very clear, and it's once you know what layer you are trying to grow on top of what, you can go back and look at the tables, find out the C's, you know what epsilons are, plug in, and you're done, right? You can calculate it exactly. Yeah.
Sigma FPI should be 0, right? That term is sigma FPI in the vertical direction.
Sigma.
Sigma FPI.
Oh yeah. I think I wrote it wrong. You're right. That's correct. So sigma. You mean sigma? This term? Sigma I epi, yeah. So let's see. No, that's a good point. So you can let me put this way. This relation that's written is this is a more general relation, meaning if I actually have something on top too, this still works. I should have mentioned that, but right. So if you put that to 0 and you plug in values, this is what you're going to get now. You have only strains here. Right. So that's right. So if sigma epi I perpendicular, if this term is 0, and you plug values in for all the others, you will get this. That's what.
So
yeah.
You have to be careful because the strain in the parallel direction determines the stress in the parallel direction and the perpendicular direction due to the Poisson stress. So
exactly right.
You will have a non-zero value if you're controlling the strain, which is what you're doing with a lot of times.
Right. So you just have to be careful when you're dealing with matrices, because you don't want to throw out something from the beginning. You go through the whole thing first, right? And then if it comes out to be 0 in the end, yes, so yeah. But physically, it's clear that if you are unconstrained, the stress in the vertical direction will be 0 in the end. But it's in the end. Don't start with that. So it should be a result. So, yeah. Okay. So you can take this matrix that we wrote, you can invert it, and write the strains in terms of the stresses. So this is just a matrix inversion, 2 by 2, take it on this side, matrix inversion. So instead of C's now, what we have are basically these Young's modulus of shear coefficients and nus, and this is the Poisson ratio. Essentially, these are, right, so if I take that expression, I flip it around, and you end up getting that the epsilons, well, I don't want to write this, I just will point this out here. So epsilon in the parallel direction and epsilon in the perpendicular direction. The strains are equal to stresses now, but here's the coefficient, here's the matrix coefficient term, right? And clearly this is some combination of the C12, C11s, and C4. Actually, this is a combination, and nu is now. So now you can write that the stress in the parallel direction, the pressure in the parallel direction, is equal to something times the stress or the strain in the parallel direction, and this nu is the Poisson ratio. 1 plus mu and 1 minus mu, right? Times stress in the parallel direction. And so this is the Poisson ratio, and the Poisson ratio at least intuitively, it is a measure of how much did the volume change after the deformation. Right, so the volume was of the unit cell was something, and then if you stretch it this way, it expanded that way. But is the volume exactly the same, or has it changed? It tries to remain very close to the same, but it's not exactly the same. So that's after the strain, and the Poisson ratio is a measure of that. How much is the deviation and things like that. Right? So that is one of the things, and the relation between the two unknowns mu and nu here are given through C11 and C2. These are two equations, two unknowns. Right? So you just convert them back and forth if you need to. Right? So, yeah. Okay, so now we get to the business of actually looking at the whole crystal structure and start asking this question: what does this mean, and how does it translate to all the energetics that we're talking about? The first thing we want to do is this is a traditional way of writing the total coherent strain that we wrote here. This is, you can call it the coherent strain, and it's typically not written in terms of C's, but you can. I mean, there's no issue if you know one or the other. It's typically written in terms of the other parameters that we just wrote, which are, you convert it into the Poisson ratio and this what's called the shear modulus or something like that. I forget. So these two, this has Poisson ratio is obviously dimensionless, right? And this mu has dimensions that are slightly different from that of pressure. But okay, so so the energy must be in joules. This is strain, dimensionless, length, so it must be energy per unit length, right, or something, joules per meter, for example, right? So now we have the coherent energy, and then if I have many layers, each of them is strained, you can do this for each layer now. If you have Poisson ratio, or if you change the Poisson ratio across many layers, you can do this. You can sum it, but then very importantly, if you have a continuously changing layer, meaning instead of a uniform composition alloy, I have a graded alloy. I start from gallium arsenide and I start grading it to 30% alg, and compositionally I change it linearly, parabolically. Then you integrate this coherent to find it, instead of summing it over each layer. So the I is kind of a thin slice here, if you might, and then you can kind of start adding it. And now the graded layers are kind of very important in 3.5s because they allow you to do quite a bit of tricks with dislocations and preventing them and that sort of thing. So yeah. Okay, so let's look at in pictures all this, the expressions in pictures now, right? So that's what we want to see. Here, so by the way, so I hope this is clear. I mean, this is nothing very fancy. We're just doing very plain mass spring physics. There's nothing new in this here. So now here's the picture where, well, I should have it upside down, but we are trying to grow this layer on top of that layer. Here, the lattice constant, hopefully you can see, is a little larger, but there's the same number of atoms this way and that way. And now we are going to look at the three important parameters here. The first important parameter is what is the lattice constant. What are the equilibrium lattice constants? Okay, and the equilibrium lattice constants here are for this layer it's written in two quantities. So for example, for substrate it's 5 angstroms. This is a representative. Actually, it can be in many semiconductors. 5 angstroms, whereas this one is 5.5 angstroms. And why are there two here? One says A perpendicular and the other is A parallel. Parallel lattice constant, perpendicular lattice constant. Thought separately, but it's a cubic crystal. So if it's a cubic crystal, then they're the same. Right? So they're the same. Now, if you were to grow this on top of that, what would be the, or rather, if you have not grown this on top of that, they're separate, then what is the strain? Right? Strain can be perpendicular and strain can be parallel. But if they're separate, strain is 0 here, strain is 0 here. No strain, right? They're separate. And similarly, what is the stress? And this stress is divided by this sort of, one of the physical parameters, and it's written in terms of that. It's just, you can convert it and write. Obviously, if they're unstrained and unstressed, there's nothing here, 0, 0. Right? And now we grow this layer on top of that and say that it becomes coherent. Right? It's completely compressed in the lateral direction, such that now see it's A here in the parallel. Sorry, it's not very clear, but essentially the A in this direction the lattice constant in this direction must become equal to 5 angstroms for that. Right? That's what we mean by, in plane lattice matching. Whereas the perpendicular has become bigger. Does that make sense? I mean, you were at 5.5 to start with. In plane became 5 angstrom because it had to strain this way, but because of Poisson ratio and volume conservation roughly, this lattice constant became longer, stretched out, right? And as a result of all this, you now know A perpendicular, A parallel. You can right away write down what is the epsilon perpendicular and epsilon parallel. Right? So that's very clear. The strain in the perpendicular direction is, you see that the lattice constant is larger in the perpendicular direction, therefore the strain is positive. Right? Larger lattice constant minus its own equilibrium lattice constant is positive. Right? Strain in the plane is negative. This is clear. It is a smaller lattice constant in this layer, right? And then that's the distribution now. Splits. And similarly, stress in the parallel direction is, whatever it is, because you know the strain, you can always find the stress now. They're related through these matrices. You'll find it. It goes negative. Very importantly, for this situation, the stress in the perpendicular direction is 0. Why? Because it's free. Right? So this is all the details of all the terms that this is in pictures what we just said. Is that clear? Yeah. And once you know that, all the energies are basically areas under essentially you take this and area under the curve and all that and square, energies are essentially just that. Once you've found what are your epsilons and stresses. So that's what. Okay, so now that is the energy cost of keeping this layer coherent. If I start increasing the thickness, h is the thickness of the layer. Let's just look at one layer. Forget about this for a second. Just one layer. It increases linearly with h, with the thickness. Right? The strain energy cost is increasing linearly with h, and that's that's the end of the story here. Right? So as we keep increasing, the strain is increasing, and obviously you have a higher and higher energy cost as you make it thicker and thicker. That's all there is to it. And now the opposing force that will that can give you an alternative or a lower energy alternative is the formation of defects now, right? And that's the whole thing. So we start looking at defects, and we had already talked a little bit about the defects in the last class, that you can have instead of, for example, let's say this layer is being grown on top of that. I think we've switched this around. This is a larger lattice constant, it's a smaller lattice constant. The substrate is a larger lattice constant. This epilayer is a smaller lattice constant here. And it's visually clear that you can actually have one missing broken bond here, right? One line of atoms that will be a broken bond here, an extra plane, right? So this has a smaller lattice constant, this is larger, so essentially it will conform, but there will be an extra plane, let's say, as an example, right? And now that's one kind of defect, right? And again, we had briefly discussed about the the vector, which says that, well, how do you find where is the defect? If you have done a TEM image or something and it's not very clear, sometimes it's very hard to pick up the defect even in a TEM image. It's hard. Sometimes you can, but sometimes very hard. So what you can do is, and this was done by very long time ago, it's called the Volterra cut and all that, because of the person who said this is a rule, and it's a nice rule. Essentially, it's just saying that you walk, say, let's say 7 lattice constants this way, 5 lattice constants that way, 7 back and 5 back, and see if you come back to where you are. Right? If you are not back to where you are, you have a dislocation inside that loop. Right? That's all there is to it, right? And then that's the way to kind of search for and detect where are the defects. Right? That's a manual way, obviously. What you can do is when you take a TM image and you get a lattice image of it, and I'll actually talk about what you do is you can do is take it's basically you can take a Fourier transform of this thing and it will tell you right away a direct image of the dislocations, and that's used to it's called a geometric phase analysis. Essentially, what you're doing is you're taking all x's here, e to the power I k dot r, and then when you kind of find the whole Fourier transform, you'll see the defect there, because as you can imagine, this is a little wrinkle in the periodicity of the crystal. It's a break in the periodicity, and Fourier transform will immediately pick it up. Does that make sense? Because Fourier picks up periodicity, right? Right, so it will pick it up and it will give you a beautiful image of dislocation and strain. So you can ask, plot me, if you take a TM image of this cross section, you can say, plot me the distances, as a function of R, in any space here, what is the distance between the two atoms? You can ask it to plot that distance between two maxima, right? When you plot it, I think you realize right away that there is a little change going on here inside. Right? So yeah. Okay, so the question we can ask is, what is the energy cost of forming these dislocations? This is an example of an edge dislocation, and this is a screw dislocation. And I think I had a couple of other pictures later, last class, which I'll, this is another way of looking at it. The edge dislocation is sort of like that, right? And the screw dislocation is like that. And what you'll notice is in the edge dislocation, these are all broken bonds all along the line. In the screw, just one here and one there. Everything inside looks perfect. Little strain and all that. So, and what we'll see right away now is there's a lot of energy. This has a lot of energy, this as compared to that, because a lot of broken bonds here, right? So, compared to the screw. Not only that, we'll see that the edge dislocation has a very strong strain field surrounding it. There will be a strain field surrounding it, whereas the screw has almost no strain around it. It's a very, very low energy defect. We'll see that now. And actually not see that. I think what you can hopefully see even visually here is, if you look at this point around it, you can see that this thing is strained. This lattice is strained. It has a much larger lattice constant here than here, than here, than here, and then it goes down as you go away from it. The strain is going down as you go away from the center of that dislocation line, right? And it's a little harder to visualize in the screw dislocation, but I think you realize that in the bulk of it there are really no defects. It's all on the surface now, in some sense, right? And then so the edge dislocation, it's very clear. There's a line of missing atoms. This is a plane that has been inserted, an extra plane, right? And so there's a line of missing atoms. There's a plane that's missing. Sorry, that's the right way. There's a plane that's missing here, right? And so there's a whole thing. So that's the length of the dislocation, and there's a vector you can write along the length, right? And remember, when we walk around here, we are going to miss a step in the end. When we come back, we won't be back to the same position, and that missing length is called the Burger vector, a Burger's vector, right? Right. That's, and then typically of the order of a lattice constant, as you can see. Now, which lattice constant, this or that, that we can figure out, but essentially, most lattice constants are very similar. It won't be the major factor for you in general. So. But what's very important is what we're going to see now is actually, I don't want to kind of what you can derive is the if the Burger's vector length, which is of the order of a lattice constant, is, let's say, edge dislocation, Burger's vector parallel, and Burger's vector. One of the very distinguishing marks between an edge and a screw dislocation is the Burger vector in an edge dislocation is perpendicular to the dislocation line. B dot L is the length of the axis of the dislocation. So so basically they are perpendicular. So right, B dot L would be 0, right? Whereas in the screw dislocation, the Burger's vector is in line with is parallel to the the axis of the dislocation. So the B dot L is not 0. And so on. Okay, so from the perspective of strain, let's look at. So here's the cost of all the coherents, and I'm going to just erase this and write down the energy cost of remaining coherent is just going back once, and I'll retain that. It basically looks as 2 times a certain material coefficient, 1 plus Poisson ratio, 1 minus Poisson ratio, times the terms I'm most interested in are H and epsilon parallel squared, right? So that's our energy cost of remaining coherent, and now we are asking what is the energy cost of not remaining coherent and forming dislocations, right? That's what we're asking now, and we'll write that down here and then compare the two, right? And find out whether the system wants to form dislocations or it doesn't, right? So, yeah. So if I look at a edge dislocation between, for example, the one that we're looking there, it has an extra plane and it's missing here. So typically this would be a picture that one would use, like a T to illustrate that. Is your substrate, here's your epi layer, let's say, right? And I think we realize there's extra plane and all that associated stuff. And it, so it'll go something like that, right? All right, you see that there. I don't want to sketch, but what I'm trying to show here is that this part of the Berger vector here is this way, right? And the line of the dislocation is going into the plane, right? Okay. And now you look at it a little carefully, and you microscopically can look at this. This region very far out is unstrained, right? Lattice constant is what it should be out here. But as you come closer to the dislocation, this part of it is strained in which way? Its lattice constant is smaller, right, than its equilibrium lattice constant, right? So it's compressive, right? This is compressively strained. What about this side here? That's tensile, right? It's bigger, right? So you see the strain is changing sign as you go around. The strain is changing sign, and you can write down the strain field as a function of r and theta, where theta could be the angle, with the with this being your axis, for example, and the strain field is going to look like sine theta, and this is something to write down, over r squared, I think, right? No, r. Sine theta over r. Yeah, it will decay as you go far out, and as 1 over r, and the angle will be sine theta. Is that clear? Or, yeah, it will decay as you go away, and I think Rocket's book had a picture of it. Yeah, there it is. So yeah, so it's the strain field is changing. It's changing. There's tensile strain here, for example, and there's compressive strain here. It's flipped upside down from what I was drawing, but you see there's a sine theta dependence, and then there's a r dependence, stretch and all that, right? So as you go around, and this is it may look like a theoretical construct, but if you actually are doing TEM and you do a geometric phase analysis, you will pick out this dumbbell shape. It's very nice. You can pick it out, and it will actually show you that, right? If you have a if you have an edge dislocation, it will show you this exact feature, right? Well, okay, we have, in our group, we do a lot of growths where we see that sort of dislocation, and that's typically a fingerprint that you got it there. Okay, so that's the strain field, and again you can do the energetics, do half kx square calculation, because you have your strain field, you can calculate the energy, right? If you know the strain, you can calculate the energy. And I'm going to just write this down, and this is also kind of an interesting problem in itself. If you have an edge dislocation, the energy cost is times this constant, material constant, times b, which is the edge dislocation Berger's vector square, over some parameters, again Poisson ratio and all that, times what you really have here is an integral of dr over r, and there's a sine theta and all that. I'm not writing that. You have effectively an integral of dr, integral of this and all that. So what you end up getting is a natural log, and I think you know very well that natural log, you can't, if you natural log of 0 is blows up, it's negative infinity, right? So there is a meaning the r, when you integrate it, you have to take care of what happens around 0. And physically, what really happens here is, obviously there's no 0 in a physical dislocation, right? I mean, there's the strain, it's not infinite, right? It's finite, right, in all places. So the way you cut it off is essentially the lower limit of the integral takes care of two things. So let me just say, so when you integrate, instead of integrating from 0 to infinity, right, obviously infinity, or you can say big R. This integral, unfortunately, has divergences both in the lower end and upper end. If you go upper end, meaning if you do 0 to infinity, I think you realize you get natural log of r, r, 0 and infinity. Natural log of infinity is infinity. Natural log of 0 is minus infinity. So it's a divergence on both ends. In physics, that would be called the ultraviolet catastrophe, infrared catastrophe. I mean, so it's a wavelength, same thing, right? So that's a mathematical problem in physics. In the real crystal, you don't have infinity, you have a size of the crystal, big R. The wafer is a certain size, right? And then in the lower level, what's going on is you have a certain cutoff. We're going to say A naught for now, and we know. So what the way one takes care of it is you write it as sorry, R naught. The R naught here, it takes care of two things. Essentially, this will be the cost of the edge dislocation because of the strain energy and all that. But the strain energy is not the only energy in edge dislocation. You also have all these broken bonds, right? Chemical broken bonds. Every bond is about an EV, about roughly, right? So you have, if you have if the lattice constant is such and the length of this is L, then you have if the length of the whole dislocation is L, then L over A is the number of broken bonds, right? Does that make sense? Every lattice constant has one broken bond, and therefore, if the energy cost of each bond is U naught, then you have L over A times U naught is another energy that you have not taken into account for the dislocation, right? And that is let me say, so all this, so you can do that, but then typically what is done is, and what is found, is that if you cut it off, if you cut off the lower length at roughly Burger's vector over 4, I'm just saying, so Burger's vector over 4, then it accounts for that energy already. Does that make sense what I'm doing? So if I take, instead of the lower limit being 0 or some arbitrary number, or one lattice constant, if I take it 1/4 of lattice constant, it also accounts for this energy scale. Because in the end, it will be plus something else, right, or minus something else, and you can absorb it in the natural log here, right? So that's and empirically, it's found that if you take 1/4 of the Burger's vector, it accounts for that. The upper end of the spectrum so R typically will not be the full size of the crystal, but if you're growing an epitaxial layer, right, the height, for example, if the dislocation is going this way or that way, typically it's of the order of the height. It stops there, right? I mean, on the surface, if the dislocation is on the surface, or it could be the full wafer if it is in the plane. So it depends. So if it's in the plane, it will be the full wafer. It can go across the whole wafer or the length. Yeah. But those are some of the energy arguments of the dislocation. Okay. So if I have a finite height, let's replace it for now, and then we'll go with that. Okay. Natural log of h for, meaning if the dislocation is going, let's say threading vertical dislocation, let's say, then the upper limit is not infinity, it's the height of the thickness of the layer. Right? That's how far it can go, right? For example. So, okay, so you have basically now two energy scales. One is this, which is for remaining coherent, and the other is this, for forming defects, right? And you can make a plot of them. The total energy is the sum of the two, right? Let me correct. That's not obvious, right? Well, these are competing right now, right? So it's not obvious how you can just combine them like that, right? So the way to combine them is to say that. Oh wait, we are already 9:50. Okay, so the way to combine them. So you'll form some dislocations, I forgot to. There's a little change here, which is this is the edge dislocation energy cost. Similarly, you can have a screw dislocation energy cost, and because there's not much strain in a screw dislocation, there's no Poisson ratio. None of that appear here. They're all gone. Right? So the screw dislocation is unstrained, and then everything else remain pretty much similar. So, sometimes you can have dislocations where there is an angle between so Burger's vector may not be completely perpendicular to the line of the dislocation. It can actually be at an angle and things like that, in which case you'll have this cosine square sine square theta. I'm not getting into all the details of that right now. Okay, so but you'll have these factors which will be kind of like here, and then what I want to get to by the end of the class today at least is to find out when is the crossover point. Where do you form? Where is that critical thickness at which you start forming defects? So that's what we want to get to. So we wrote down this. Let's say this is our expression now for dislocation energy cost. It's like this, except if you have an angle, you have this other cosine factor on the top. But I'm not writing that right now. And if you look at it and look at it a little carefully, it will look very similar to the potential energy of a point charge, for example. actually no, this is the potential energy. For example, the potential energy of a point charge in Coulomb potential energy is what, like it's Q over 4 pi epsilon times R, right? But if you at a distance R from the point charge, but if you take a line charge, right, and you go a distance R from it, right, as what's the potential here, then it will look like is basically, if the line charge density is lambda, then it's lambda by 2 pi epsilon natural log of, you know, R over R naught, where R naught is kind of the radius of the cylinder. You've probably seen that. And you see this is actually exactly similar. There's no difference, right? And in fact, the analogy is much further than that, goes much further than that. You know, if you have one dislocation that's here, you have another dislocation that's there, how do they interact? They actually interact very much similar to how charges interact. They'll, you know, if this dislocation has a Burgers vector this way, that has a this way, they will actually attract. They're like, unlike charges, the strain fields will try to attract them. And if they're opposite, they'll repel, and all that kind of fun stuff. I mean, basically, the whole electrostatic argument carries over here as well. So, in fact, the potential energy, so the strain field plays the role of the. Okay, so there's an analogy. I'm not trying to go much deeper. Perhaps in the next class, I want to finish up the energy argument right now. So here, what you can say now is, look, I have two competing effects. I can form defects, or I can remain coherent. But if I form defects, I have to introduce the dislocations in a nice way. I can't just say that I'll form one defect, because it's not going to be like that. You will probably form an array of dislocations, right? And here's a rule of thumb. How many dislocations are you going to form? Right? What will be the density of dislocations you are going to form? And that's very easy to answer. Basically, if this layer here has to completely relax, right? If it has to completely relax by the formation of a number of dislocations here, right? So each dislocation relaxes it by roughly the order of the Burgers vector, right? That's the length it gives you, right? And the total length is like some wafer size, big L, let's say, right? So what will be the spacing between dislocations? That should be pretty trivial to answer, right? Does that make sense? I mean, basically, we already know the equilibrium lattice constants of the two, right? Therefore, what should be the spacing between dislocations so that you are completely relaxed? And here's the number, and you can think about why it should be the spacing between dislocations. Spacing should be of the order of the Burgers vector over the amount of strain. How much strain you have. This should be the case, and you can see that if you have that many dislocations, or this is the dislocation per unit length, right? Per, say, 10 to the power 5 or 10 to the power 6 per inverse centimeter, then the top layer can completely relax now. Right? So that's it. In numbers, if your strain is 1% lattice mismatch, then there will be a dislocation every 100 unit cells, roughly. Right? Does that make sense? If strain is 10%, it will be every 10 unit cells. There will be a dislocation. Right? And if it is, let's see, here's an example, a beautiful one, where this is indium antimonide on gallium arsenide. So, and then here's a TEM image. It's kind of hard to see, but yeah, well, these bright spots you see are the kind of the strain fields around the dislocation. This is the strain field. It's okay, and the spacing here is basically, you can do what I just did here. This is the lattice constant roughly, right? So this is, so 1 over epsilon is a very nice crude number, rough number for spacing of dislocations. And if it's 11% lattice mismatch, you will see a dislocation every 10 or 10 lattice constants, or something like that, and you see it here. So, yeah. Now, not all the time it will be like this, but generally it's a good number. I mean, so good estimate of what's the spacing between dislocations. So once you form the spacing between the dislocations, let's say the spacing is a length, and the density of that is 1 over that, so epsilon over b would be the density, the linear density of dislocations. How many dislocations per unit length? Is that clear? That's just this, nothing fancy right now. We're just doing very simple, intuitive numbers. And if your spacing is not equal to that, meaning if your spacing between dislocations, this is what it will be necessary to completely relax. Right? Let's say I'm not completely relaxed, I'm only partially relaxed. Right? Then your spacing between the dislocations will be much larger. Right? In the limit, when there's no relaxation, spacing is infinite. There are no dislocations. Right? Does that make sense? Okay, so that's the parameter we're introducing now. Rho misfit dislocation. That's the spacing between dislocations. It's a parameter that we're introducing because these two things are going to go against each other, right? And then depending upon the spacing, this will win or not win. Right? So and we want to find out what both things, the energy minima as well as the spacing now. Okay? So the total strain, if your spacing is not for the complete relaxation case, but is some finite, so the amount of strain misfit misfit that is taken up by the dislocations is the unit the density of dislocations times the edge, the Berger vector along the in-plane Berger vector. So that's the amount of misfit that's taken up by dislocations. The amount of misfit that's left over that has to be taken up by coherence, by the strain energy, is just the total minus that. I mean, nothing real fancy, it's just standard stuff, right? And now you write that my coherent energy is not the complete strain, but what is left over after the dislocations are formed. Right? So that minus due to this misfit due to dislocation. So your spring, doesn't have to stretch all the way, right? Because part of it has formed because of dislocation. It stretches a little less. Right? So you have that square. So essentially this epsilon here, it gets modified. I mean, that's all we are saying. It gets the total minus something due to dislocations, right? And that depends on what is the density of dislocation. Right? And then it has its own here, which is the dislocation cost. Obviously now depends on what's the density of the dislocations, and every dislocation has that energy cost. Every single one has this cost. So okay, so does that make sense? I mean, we're partitioning the energy into this and that, right? And we take the total energy of the system. The total energy is basically the coherent part, which is due to the strain, and then the part due to dislocations. Let's see, so the dislocation. Okay, let me just say, so there are twos, and all these are very, one can explain very clearly, and the two comes about because the picture we're looking at now is if it had, for example, a dislocation in this direction and dislocation in that direction, x and y. So there's a spacing along x, there's a spacing along y, right? So you form these dislocations, so there are two axes along which there are dislocations formed along each axis. Just like we're summing it for epsilon along x, epsilon along y. Same thing here. You sum the whole thing over, and what you get in the end is total energy as a function of the dislocation spacing or density of dislocation, and obviously the height, h. Right? So the height term here is increasing linearly. Here it's increasing logarithmically, right? And you make a plot of this. Here's the plot. This thing is because of coherence. It goes as parabola with the number of dislocations, or the density of dislocations. It's pretty clear. It's just a square of that. Its minima is not at 0. It's shifted parabola. It's somewhere there, right? Whereas the energy of dislocations, that term, it's very faint here, but that thing really just depends linearly on the density of dislocations. More is the density, more is the energy of that. So that it's a little hazy here, but it goes like that, right? And you sum the two, you sum the parabola with this. So obviously that 0 point remains here, but this is the total energy of the whole system now. Right? So this has been plotted at 90 angstrom, meaning the h is 9 nanometers. This h is 9 nanometers, right? And what you see is the minima here is on the parabola. The minima here is at 0 dislocation. There's no dislocations, not a single dislocation. So this remains coherent. This wins, no defects. So as long as you add this thickness, no problem. The moment you go to, say, example here, 130 angstroms, you see the minima now has shifted here, right? And that means this obviously has formed dislocations now, as you can see. Right? Is that clear? The minima shifted, so they form dislocations, and now you want to find what is that critical thickness. I think you just take a derivative of this, and equate it. If there's a minima which is not sharp, you'll pick it up, and here's the critical thickness. Essentially, it comes from this expression, right? And this is called the Matthews-Blakesley law, or Matthews-Blakesley relation, not law, but relation, and it has all these things. Basically, this is a critical thickness. Just to be careful, it also appears here, so it's not a simple formula. You have to solve it. It's a transcendental equation. You just have to solve it, and you can plot it. Here are the plots for silicon germanium alloys, and this is the formula. Here are the experimental data, and it's actually reasonably good. For many situations, it works pretty well. Right? So, okay, so let's stop here today, and in the next class, hopefully tomorrow afternoon, we'll finish up the discussion on dislocation, specifically what are the numbers. I think I gave you some reasons today how they form and what are critical things. Next class, we'll look at the numbers, how do they affect electronic, photonic properties and all that. That's something we'll look at, and how, if you cannot avoid them, how can you make good use of them? That's really what we're going to talk about in the next class, and then move on to the next topic. Okay? All right, good. Thanks.